In section 5.2, we're going to talk about the definite integral. Now in section 5.2, we're going to go over some general terminologies first, but we're going to go over the formal definition of what it means to take an integral. And I'm going to work several examples for you using the formal definition. So here is the integral from a to b of a function f of x dx, right? So a and b are what we call the upper limit and the lower limit. So b is going to be the upper limit of our integral, and a is going to be the lower limit of our integral. Okay, and we're going to integrate f of x. Now dx, this f of x, actually the f of x is called the integrand, right? It's what we're taking the integral of. Dx is our variable of integration. It's what we're integrating with respect to. So anytime you write an integral, right, a definite integral, we need all these parts, right? We need an upper and a lower limit. We need our function, and we need to know with respect to which variable are we integrating. So when we calculate the definite integral, we're finding the area under the curve. So I've drawn a random function here, right? Some of the function is above the x-axis, some of it is below. But calculating the integral is still calculating the area. So I've kind of colored in the area above the x-axis with these diagonal lines. And then I've colored in the portion of the area below the x-axis with some dots. So the area above the curve I'm going to call capital A sub 1. And below the x-axis, we're going to call that area capital A sub 2. So when we calculate the area under f of x with respect to x from a to b, what we're going to do is that the area above the x-axis is counted as positive area, and the area below the x-axis is counted as negative area. So we're going to calculate all the positive area, and then we're going to subtract from it all the negative area. Right? So just so you know, sometimes if our graph is completely below the x-axis, or more is below than above, we're going to get a negative area. And that's possible because there's just more area below the x-axis than above. All right, so here's the formal definition of an integral. So when we integrate from a to b of a function with respect to x, right? We learned how to calculate using rectangles, right? And so we would use 4 rectangles or 6 rectangles, but the more rectangles we use, the better off. And so what we're going to do is we're going to use infinite number of rectangles. So the formal definition is the limit as n goes to infinity of an infinite sum here. I equals 1 to n. And then all of our rectangles have a height and they have a width. So the height of our rectangle is going to be the function evaluated at x sub I star. And then the width of our rectangle is going to be delta x. I really want you to see this as the height of the rectangle times the width of the rectangle. Right? So we're just calculating in number of rectangles, and we're letting n go to infinity in the formal definition of an integral. Right? So height times width is going to give us the area of each rectangle. Now, delta x, right? Remember what delta x is? The width is the total distance divided into n parts. So we're going to do b minus a divided by n here. That's always what delta x should equal. Now x sub I star is not a left-hand endpoint, not a right-hand endpoint, not necessarily a midpoint. It's any point in between x sub 0, x sub 1, right? X sub 1 star would be any point between x sub 0 and x sub 1. X sub 2 star would be any point between x sub 1 and x sub 2. And so when we're using infinite number of rectangles, the small difference between the left endpoint, the right endpoint, and the midpoint is really kind of negligible. All right, so we're going to have to find a formula for x sub I star when we use this formal definition. All right, so we're always going to have to find its formula. All right, so first I'd just like to get used to this formal definition. So I'm going to give you some limits, and we're going to write it as its integration, okay, as its integral form. We're just going to go here from the right back to the left just to kind of get used to seeing this. And then I do have at least 5 examples of how to calculate this integral using the formal definition. So first, right, let's write each of these as a definite integral. So the first example, the limit as n goes to infinity of the sum from 1 to n. We're going to do x sub I times ln of 1 plus x sub I squared times delta x. Right, and so we're going to let our area go from 2 to 6. So when they give you an interval like this, they're kind of telling you what the upper and the lower bound is, right? And so, and they didn't really give us the formula, they just put delta x in there, right? So what we're going to do is we're going to write this as an integral. So my first clue is 2 is the lower bound and 6 is the upper bound. So this is the integral from 2 to 6. and now I need to know what the function is. Okay, so when we calculate the height of these rectangles, we're doing x sub I star inside the function. Now this example doesn't have x sub I star, it just has x sub I. But we're plugging those x sub i's into the function. And so what would the function look like with just no x sub i's? Well, the x sub I is simply x. And so we're going to get x ln of 1 plus x squared. This is our function. Because if I plugged x sub I in there, I would get this part. Right? So this is kind of like the height of our rectangles. Now delta x is the width. Right? And the width of our rectangles is just telling us we're finding the width with respect to x. So delta x in the integral form becomes dx. Right? So pretty fairly simple. This is the formal definition. This is the integral form. Right? So another example, if we had the limit as n goes to infinity, the sum from 1 to n, square root of 2 x sub I star plus x sub I star squared times delta x. And this limit is going from 1 to 8. Okay, so A is 1 and B is 8. So again, okay, the first clue is 1 is going to be our lower limit and 8 is going to be our upper limit. So if I was to write this as an integral, we're going to integrate from 1 to 8, right? And now what's the function, right? The function is take the x sub I stars out and just put x in there. So this is the integrand then would be 2x plus x squared, right? And delta x becomes dx, right? Fairly simple here. So this one, okay, last example here of this type, it's not going to give us an interval here. Okay, so we're going to have to figure out what the upper and lower limits are. So we're looking at the limit as n goes to infinity. I equals 1 to n. We're going to do x sub I cubed plus x sub I sine x sub I times pi minus 0 over n, right? So I wrote pi minus 0. Now, if they just wrote pi, it would be a little bit more complicated. But delta x is always b minus a divided by n. So this is another way of the question giving you the upper and the lower bound. So the upper bound is going to be pi, and the lower bound is going to be 0. So if they just put pi here, we know the difference between our upper bound and our lower bound is a distance of pi. So we could have done pi to 2 pi or 2 pi to 3 pi. Okay, but the simplest way is to go from 0 to pi. So I'm going to take this hint here. This is the delta x part, right? b minus a over n. So I know that 0 is the lower limit and pi is the upper limit, right? Now what's the function? Okay, we're going to take the x sub i's out and just put x's in there. We're going to get x cubed plus x sine x, right? And then every single integral needs a variable of integration, and since our variable is x here, we're going to integrate with respect to x, all right? So now let's go, okay, let's given this integral here, let's calculate the value of this area using this infinite sum of rectangles. All right, so the directions say calculate the area using n subintervals. So we're going to do the area from 0 to 3, x cubed minus 6x dx, right? So 0 is our lower limit, 3 is our upper limit, and our function is x cubed minus 6x. So we want to calculate the area between the curve and the x-axis, right, using n subintervals. So this is telling you to use the definition, right? So the definition says we're going to do the limit as n goes to infinity, and we're going to sum n rectangles, and each rectangle is going to have a height at f of x sub I star, and each rectangle is going to have a width of delta x. Right, so here's where we have to find the formula for x sub I, and we have to calculate what delta x is for this problem. Right, so I'm going to do a little bit of scratch work over here. I'm going to calculate both of those formulas. So delta x is b minus a over n. So in this case, we're going to do the upper limit minus the lower limit and divide that into in subintervals. So our delta x is 3 over n, right? Now we have to figure out what x sub I star is. And what I like to do is I like to calculate the first couple subintervals, right? So I'm going to start with x sub 0. X sub 0 is always a, right? So our first x sub 0 is going to be 0. Now if I were to calculate x sub 1, we're just going to add delta x to it. So we're going to get 0 plus 3 over n, which is 3 over n. And if I were to calculate x sub 2 is delta x distance away from x sub 1. So I'm just going to add delta x to x sub 1, and so I'm going to get 6 over n, right? So x sub 3 is, again, another delta x away from x sub 2. So if I do 6 over n plus 3 over n, I'm going to get 9 over n, right? So using this pattern, right, what is x sub I? Right? Each time we're starting at 0 and we're adding 3 over n. So the pattern then would be 3i over n, right? So if I had x sub 0 star, I'd plug 0 in and I would get 3 times 0 over n, which is 0. If I had x sub 1 star, I would plug 1 in for the I and I would get 3 over n. If I were to use x sub 2, right, I would plug 2 in for I and I would get 6 over n. 3, right, I would plug 3 in for I and get 9 over n. So it is kind of important to check your x sub n, right? So, or x sub n in this case is we would plug in n for I, and so we get 3n over n, which is equivalent to 3, right? So x sub n should be our last end point, and it is, okay? It should be our upper limit of our integral, okay? And it is indeed n. So you always want to make sure your formula works for the last term as well, all right? So now what I'm going to do is I'm going to plug those in, okay? I'm going to plug x sub I star n, right? 3i over n, and I'm going to plug delta x in. So now I've got the limit as n goes to infinity of the sum from 1 to n. And we're going to plug our x sub I star in there, which is 3i over n. And then we're going to multiply that times delta x, which is 3 over n. Right? So calculate your formulas, plug them into your definition here. So in order to plug in 3i over n into our function, here's the function, x cubed minus 6x. So I'm going to plug 3i over n into each x here, right? So now I have the limit as n goes to infinity of the sum from 1 to n. If I plug 3i over n into the function, I'm going to get 3i over n cubed minus 6 times 3i over n. And all of this is multiplied times delta x, which is 3 over n. So here's the height of all of our rectangles, and here's the width. So now we have this infinite sum, and we worked through how to calculate all those known sums, right? So what I like to do is I like to go ahead and cube this, distribute this, and also multiply the 3 over n through here. So I'm going to kind of clean this up, okay? Expand it out. Right. So 3i over n cubed is 27i cubed over n cubed. 6 times 3i over n is 18i over n. And then I still need to multiply that by 3 over n. Right? So I'm going to go ahead and distribute the 3 over n next. And so 27 times 3 is 81 I cubed over n to the 4th, because we have n cubed times n. And then 18 times 3 is 54. So we're going to get 54I over n squared. Right? So we want to calculate first this sum. And then we'll take the limit. So when we calculate the sum, remember we like to remove all the constants out. So we just have the sums of i's. Okay, so that's what I'm going to do next. So we still have the limit as n goes to infinity out here. And then I'm going to sum each of these terms with the constant pulled out front. So when I look at 81 I cubed over n to the 4th, 81 over n to the 4th is a constant because it doesn't have an I in it, right? So I'm going to do 81 over n to the 4th times the sum of I cubed minus. Now in the next term, I'm going to sum the I only, and 54 over n squared is going to be the constant because it's not going to change with each term. Right? So I get 81 over n to the 4th times the sum of I cubed minus 54 over n squared times the sum of I. Right? So we have those formulas, right? The formula for I cubed is a known sum, right? And we did that in the appendix F. The sum of I is a known sum. So I'm going to replace that summation with its formula. So now I get the limit as n goes to infinity, 81 over n to the 4th times the formula for I cubed was n times n plus 1 over 2 squared, right? Minus 54 over n squared times the sum of I, and the sum of I was n times n plus 1 all over 2, right? So now what I like to do is I like to expand this or cancel this as much as possible, okay? So let's go ahead and do some work here. It looks like when I square this, I'm going to get n squared, right? So I'm going to let n squared cancel with an n squared down here. So I'm going to go ahead and cancel this n off. I'm going to change this to a 2. Now remember, we still have n plus 1 squared in there. And when we square 2, we're going to get 4. But 4 doesn't divide 81, right? So I'm going to get the limit as n goes to infinity. 81 over times n plus 1 squared over 4n squared, okay? Because this n squared canceled, this is still squared, 2 squared is 4, okay? So that's how I get that term simplified. The other term, I'm going to go ahead and let n cancel with n here, and I'm going to go ahead and let the 2 cancel with 54, right? So I'm left with 27 n plus 1 over n, right? So there's the sum, and I'm not going to simplify that any more than this, right? So here's where we evaluate this infinite limit. And if the powers of n match, remember that limit as n goes to infinity is just the horizontal asymptote. And the horizontal asymptote, if the degree of the top is equal to the degree of the bottom, is just a ratio of the leading coefficients. So if I were to multiply out n plus 1 squared, I get n squared plus 2n plus 1, right? And then we distribute the 81 through there. But the coefficient here, the leading term here would be 81n squared, right? And on the bottom we have 4n squared. So the highest power on the top and the bottom is both 2. And so when we calculate this infinite limit, we're just going to get the coefficient of the top over the coefficient of the bottom. So I'm not going to do a whole bunch of work here. I'm just going to write that the first term gets 81 over 4. Now the same thing is going to happen over here. If I were to multiply all this out, I get 27n minus or plus 27. And on the bottom we have an n, but the powers of the top and the bottom are equal. And so the infinite limit is just going to be the coefficient of the top over the coefficient of the bottom. And so we're going to get minus 27. Right, so in order to calculate this, we will I'm just going to plug it into the calculator. All right, so if I get 81 divided by 4 minus 27, get negative 6.75. I'm going to go ahead and change that to a fraction, and I'm going to get negative 27/4. Right, so the area between 0 and 3 of x cubed minus 6x is negative 27/4. So here's one of those cases where there's more area below the x-axis than above the x-axis. So I want to kind of show you that. So if I were to type the function in, x cubed minus 6x, and graph it, okay, between 0 and 3, 0 and 3, all of this area is below, and then we just have a little sliver of area above, and so that is why we're getting a negative result there. Okay. Let me zoom out so you can see the whole process. Right, so first we're going to calculate delta x and calculate our formula for x sub I. We're going to plug them in. We're going to work out our sums, and then we're going to take the limit of those sums. See if I can get it looking a little bit better for you. All right, so I'd like to work a few more. Okay, I have 1, 2, at least 3 more that I'd like to do with you. Okay. So let's do the integral from 1 to 2 of x cubed dx. Right. So what's the area? Okay, between x cubed and the x-axis from 1 to 2. So x cubed between 1 to 2, the area is above the x-axis, so our answer should be positive here. Right? So the first thing I'm going to do is I'm going to write the formal definition. This is the limit as n goes to infinity of the sum from I equals 1 to n f of x sub I times delta x, right? So now let's go ahead and figure out what delta x is, right? So delta x, the upper limit minus the lower limit divided into n subintervals. So we're going to get 1 over n here, right? And then let's find a pattern for what x sub I is, right? Or x sub I star. So x sub 0, right? Where is our first subinterval? Where does it start? X sub 0 is always a, right? So we're going to start at 1. And then we're going to move to x sub 1, right? So x sub 1 is delta x units away from x sub 0. So we're going to get 1 plus 1 over n. Where's x sub 2? Right? X sub 2 is 1 over n units away. So if I do 1 plus 1 over n plus 1 over n, I'm going to get 1 plus 2 over n, right? Because 1 over n plus 1 over n is 2 over n. So x sub 3, 1 plus 3 over n, correct? Right? X sub 3. If I add 1 over n to this, I'm going to get 1 plus 3 over n, okay? So usually it takes me to x sub 2 to figure out what the pattern is. The third one just helps solidify it. So what is x sub I? right? How many delta x's are we adding? We're going to start with 1, and then we're going to add, x of 1 is 1 over n, x of 2 is 2 over n. So we just need I over n, right? Because if I replace I with 1, I get x of 1. If I replace I with 2, I get x of 2. And if I replace I with 3, I get x of 3. Now what is x of n? Right? Just double check your formula. Right, so if I plug n in there, I'm going to get 1 plus n over n, which is 1, right? And 1 plus 1 is indeed 2, right? X of n should always be equal to the upper limit, right? X of 0 is your lower limit, x of n is your upper limit, and it should work out with your formula if you figured it out right, okay? So I'm going to replace in the limit here. I'm going to replace x sub I star with the x sub I that I found, right? And I replace delta x with 1 over n. So I'm going to get the limit as n goes to infinity of the sum from 1 to n, x sub I star. I'm kind of not using the star here, right? But we're just going to use x sub I. We're going to plug 1 plus I over n into this function, right? And then we need to multiply that times delta x, which is 1 over n, right? So I'm going to need to plug 1 plus I over n into the function in order to calculate this limit. Right? Bring along the limit, bring along the sum. Now plug 1 plus I over n into the function. So we're going to get 1 plus I over n cubed times 1 over n, right? So here's where that Pythagorean, I'm sorry, not Pythagorean, the Pascal's triangle really helps, right? We are going to have to cube this out, right? So remember the third row. Well, if we don't include this one, this is our coefficients for x plus h squared, and these are our coefficients for x plus h cubed, right? So my terms are 1 is the first term and I over n is the second term. So the coefficient is 1, and then I'm going to multiply that times the first term cubed, plus 3 is the next coefficient. And so we're going to do the first term squared and then the second term to the first power, right? Plus 3 is the coefficient. Now we're going to do the first term to the first power and I over n squared, right? Plus 1 is the coefficient, and then we're going to put all the power on our second term there, I over n cubed, right? So if you remember with the x's and the h's, right, the power of the x started at 3 and went down, and the power of h started at 0 and went up, right? So each of our terms the exponent should add up to 3, okay? So if I multiply all this out, I'm going to get 1 plus 3i over n plus 3i squared over n squared plus I cubed over n cubed, right? It's still a little bit of work, but this is much easier and much simpler than foiling and trying to keep track of all of our like terms, okay? So 1 plus I over n cubed is all of this, all right? So now what I need to do is I need to multiply this polynomial here by 1 over n. So I'm going to do that when I write it down here. All right, so if I multiply 1 times 1 over n, I get 1 over n. If I multiply 3i over n by 1 over n, I get 3i over n squared. I should have scooted that down a little bit. Plus 3i squared over n cubed plus I cubed over n to the 4th. right? So there is our function at x sub I times delta x all multiplied out, right? So now we want to evaluate the sums. And this is where we distribute the sum to each one of our terms, factoring out those constants and leaving the i's in there, right? So we haven't yet evaluated the limit. So the limit is still out there, okay? Now in this first term, 1 over n doesn't have an I. So it's like we're calculating the sum of just 1. So I'm going to do 1 over n times the sum as I equals 1 to n of 1, right? I'm going to still take that constant out, but it leaves a 1 in there. The coefficient here is 3 over n squared times the sum of I. The coefficient here is 3 over n cubed times the sum of I squared. And then the coefficient here is 1 over n to the 4th times the sum of I cubed, right? So the sum of 1, I squared, I cubed, all have known formulas here, right? So if we add up in ones, this sum here, we're just going to get n, okay? Let's go ahead and write that down, right? Substitute all those known formulas for those sums. So the first term, we're going to get 1 over n times the sum of 1 is n. The next term, we're going to get 3 over n squared times the sum of I, which is n times n plus 1 over 2, plus 3 over n cubed times the sum of I squared, which is n times n plus 1 times 2n plus 1 over 6. Make sure I remember that. Oh, I believe that's right. God, I hope that's right. Let me make sure. Yes. Okay. Make sure you keep those sums handy so you don't make a mistake here. All right. Plus 1 over n to the 4th, and the sum of I cubed was n times n plus 1 over 2 quantity squared. Okay. So I'm just replacing these summations with their formulas. So now I can clean this up so that I can evaluate the limit just a little bit easier. All right, so cleaning up the first term, I can let the n's cancel and I'm just left with 1. Cleaning up the second term, I can let 1n cancel and I'm left with 3 times n plus 1 over 2n. Notice that the degrees are the same here, right? So evaluating the limit is going to be pretty simple. Now in the third term, I'm going to let the 3 cancel with the 6, right? And then I'm going to let 1n cancel with an n here. And so I get n plus 1 times 2n plus 1 over 2n squared, okay? And then the last term here, remember these are squared, okay? So n's, I'm going to go ahead and let n squared cancel with 2 of these n's. So I'm going to cancel this to a 2 and cross this off. So I have n plus 1 squared over 4 n squared, right? Because we have to square the 2 as well. All right, so all of these degrees match, right? This one is just a constant, but we have degree 1 on top, degree 1 on bottom. Here, if I were to multiply this out, I'd have a second degree on top and a second degree on the bottom. The last term, second degree over second degree. So every single one of these fractions, the degree of the top matches the degree of the bottom, and that will happen, okay, if you've done everything correctly. So when I calculate this infinite limit, because the degrees match, we're just going to get the leading coefficient over the leading coefficient. So I'm not going to write the limit because I'm evaluating it now. The limit of a constant is the constant, right? Plus this limit here, the degrees match. So I'm going to get 3 over 2 plus, now this one's the tricky one, okay? What would the leading coefficient be? If you were to multiply this out, you would get a 2n squared, correct? Plus blah, blah, blah. So I have a 2n squared up top, a 2n squared on the bottom. So the leading coefficient over the leading coefficient simplifies to 1, right? Because we had a 2 over 2. And then here, the leading term is going to be n squared on top. Leading term is 4n squared on the bottom, so I'm going to get 1/4 here, right? So the final area would be when we add these together. And we're going to get 15/4, okay? All right, there's your second problem. All right, worked all the way out. I hope it's getting a little bit better. All right, calculating delta x and then x sub I, and then just doing all the grunt work, if you will. All right. Let's do another one. Okay. So calculate the integral using the definition. So let's do the integral from -1 to 3 of 1 plus 3x dx. Now, the ones that are harder are the ones that don't start at 0, because it makes the FOILing process just a little bit more detailed, all right? So I went to Pascal's triangle when I multiplied it out. But the process is still the same. So I'm trying to work as many integrals where the lower bound isn't 0 as possible. All right. So using the definition, we're going to do the limit as n goes to infinity, infinite rectangles of the sum of the height of our rectangles times the width of our rectangles, right? So this is just the sum of all the areas, okay? A sum of all those infinite rectangles. So let's figure out what delta x is, right? Delta x, the upper limit minus the lower limit divided into n subintervals. So I'm going to get 3 minus a -1 over n, which is 4 over n. Right? So our delta x is 4 over n. Now, what is our x sub i's, right? Start with x sub 0, okay, and then find a formula. So x sub 0 is always your lower limit, right? X sub 0, we're starting this at -1. And so x sub 1, we're going to add delta x to that. So -1 plus 4 over n. X sub 2, we're going to add delta x to x sub 1. So if I add 4 over n to this, I'm going to get -1 plus 8 over n, right? And so at this point, I usually can find x sub I, okay? Because we're just adding 4 over n each time. So we're going to get -1 plus 4i over n, right? Just multiply, we're just adding I delta x's, okay? So if I plug 0 in there, into this formula, I'm going to get -1. If I plug 1 in for I, I'm going to get x sub 1. If I plug 2 in for I, I'm going to get 8 over n, which is x sub 2. Right? So just really quick, let's double check x sub n to make sure we get the upper limit of our integral. So if I plug n into our formula for I, right? So x sub n, I'm just putting an n there. So I'm going to get negative 1 plus 4, which is 3, okay, which equals our upper limit. So this kind of tells me that I did it correctly, right? Your last term should work with your formula, okay, and all your other ones before too. So now that I know I have the correct formula for x of I, I'm going to plug it in. So I'm going to get the limit of the sum, right? Let me just plug x of I into my function, right? So I'm going to get 1 plus 3 times x of I. And then all of this needs to be multiplied times delta x, which is 4 over n, right? So I kind of skipped that intermediate replacing x of I and delta x and just kind of putting it into the function there, right? So here's my function evaluated at x of I times delta x. So now I like to multiply all this out, okay? Just to help the sums go a little bit easier. So I'm going to do 1 minus 3 plus 12I over n times 4 over n, right? So first distribute the 3. Okay, 3 times negative 1 is negative 3. 3 times 4I over n is 12I over n. So this I can add together to get negative 2, all right? So I have negative 2 plus 12I over n, and now I need to distribute the 4 over n to both of those. So I'm going to get the limit as n goes to infinity of the sum from 1 to n, negative 8 over n plus 48I over n squared. Okay, so there it is, all multiplied out. Okay, so now let's sum each term, factoring out the coefficient, leaving the i's. So in this first term, negative 8 over n is a constant, if you will. And then we're going to sum a single 1. Plus, in the next term, 48 over n squared is the constant. And we're going to sum I. Right? So now I'm going to replace those summations with their known sums. Right? The sum of 1 is n, and the sum of I is n times n plus 1 over 2. So I'm going to get the limit as n goes to infinity, negative 8 over n times n plus 48 over n squared times n plus 1 over 2. Right? Just replace those sums with their known formulas. Right? Clean it up. I'm going to go ahead and let the n's cancel here and get negative 8. On the second term, I'm going to let the n's cancel and then reduce the 2 into the 48 to get 24. So I'm going to get 24 times n plus 1 over n. Okay. So again, the degree of the top, if I were to multiply this out, is equal to the degree of the bottom. So when I take the limit, I'm just going to get the coefficient of the top over the coefficient of the bottom. And the limit of a constant is a constant. So I'm going to get negative 8 plus 24, which gets a sum of positive 16. Okay? So I hope this is enough. If not, I will hold some extra sessions with you and help you work through where you get hung up. But I would like to show you another way to calculate an integral, because this section also wants you to be able to use geometry to calculate the integral, and I think this is a perfect example to show you that. All right? So I'm going to pick this same integral and use geometry to calculate the area, and we should get an answer of 16. All right? So let's use geometry to find the integral. So we're going from -1 to 3 of 1 plus 3x dx, right? So we can do this if we have linear functions. We can't do this if we have like curvy functions. And so what we're going to do is we're going to graph 1 plus 3x, and we're going to find the area between the graph and the x-axis, right? So if I were to graph 1 plus 3x, I'm going to have to be really careful here. Right, between -1 and 3. So let me plot those points. If I plug -1 into here, I'm going to get 1 minus 3, which is -2. So here's my first point. If I plug 0 in there, we're up at 1. If I plug 1 in there, we're up at 4. And if I plug 2 in there, we're up at 7. And if I plug 3 in there, we're up at 10. Yeah, I did not plan this out very well. All right, so here is the linear function. Okay. And it goes on and on forever. You know, this probably isn't the best example. Oh well. All right, so we want to calculate the area between -1 and 3, right? And we want to use geometry. So if I look at the area, here I have an area below the x-axis, and I have an area above the x-axis. So remember, we want to calculate the area, the +1 minus the -1. So I need to calculate the area of this triangle. So the height is easy, right? The height was 10. Okay, now this base here is a little bit harder because it's not just 3, because we have this little sliver here. So what is the x-intercept, right? If I take 1 plus 3x and set it equal to 0, I'm going to get -1/3, okay? So this is -1/3, right? So this distance here is 3 plus 1/3. Okay, I hope you're okay with that. So the area of the positive triangle, the area above the x-axis, is going to be 1/2 the base times the height. And then we want to find, let's go ahead and do that. I'm going to call it a sub 1 because that's what I called it before. 1/2 the base times the height. Now, to multiply this out, I probably should change this to a mixed fraction. I'm sorry, an improper fraction. So 3 times 3, 10 thirds times 10. So I'm going to get 100 over 6, right? Which would simplify to 50 thirds. All right, let's go with that. This is not the best example, but we can do it. All right, so let's calculate this area below the curve. So we want to know the base times the height. All right, now the base stops at -1, and if this is 1/3, okay, then this distance is 2/3, right? It's negative, but it's still 2/3. And then the height is 2, right? So a sub 2 here, 1/2 the base times the height is going to get us 2/3. Okay? So the integral here using geometry, we're going to do the area above the x-axis minus the area below the x-axis. So a sub 1 minus a sub 2, 50 minus 2/3 is 48/3. Oh, thank God that worked out. All right, 48/3 is 16. All right, so we can use geometry to calculate these areas as well. All right, let me do one more using, or maybe, yeah, I'm sorry this video is so long. Pause it, take a break, okay? But I just want to get it done. All right, let's do another area. Okay, the area between 0 and 3, x minus 1 dx. Right? Using geometry. So what you want to do is you want to come up with a graph. Right? Where is this line? So if I plug 0 in for x, the graph is at -1. If I plug 1 in, I'm going to get at 0. 2 in, we're up at 1. And if I plug 3 in for x, we're up at 2. Okay, so here is the graph of x minus 1, right? It's a linear function. The y-intercept is -1, slope of 1. Here we go. Okay, here's the line. But we want to calculate the area just between 0 and 3. So again, here we have a little bit of area below the x-axis, and then we have some area above the x-axis. And we want to calculate both of those areas and do the positive one minus the negative one. So this one's a little bit easier, okay, because these triangles don't have fractions. The height of the positive triangle is 2. The width, or the base of the positive triangle is 2. So a sub 1 is going to be 1/2 the base times the height. Half of 4 is 2. All right. A sub 2, the area below the x-axis here, the height is 1, the width is 1, 1/2 base times height is 1/2. And so our total area, the positive area minus the negative area, 2 minus 1/2 is 3/2. Okay. So in 5.2, you're going to be calculating integrals using the definition. Okay, you're going to be given the definition and you're going to have to find the integral, and then you're also going to be using geometry to find the integral.